we continue with where we left off on Monday. We went over, introduced the scientific notation. We talked about examples of using the scientific notation for big numbers. I'm going to show you a slide here just to kind of by way of a review. This is some of the stuff that we talked about on so this slide says getting a sense of mass, and then it gives you a little bit of a rundown of different numbers. And this is some of the things that we were talking about on Monday. Is it a little too bright? It's okay. Can you catch it over there? Maybe not the whole thing. Try one of them. This one here. Yeah, maybe keep those ones up, and then we can, I think that's better. So over here, it starts out kind of in the small arena of things. Things that are very, very light. Okay. And then you see here the use of scientific notation. So it starts out mass of the electron, 9 times 10 to the minus 31 kilogram. You see how useful the scientific notation is, even for very light things. Then you get the proton, 2 times 10 to the minus 27 kilogram. Very, very tiny little mass. Okay, then you get bigger things, DNA molecule, 2 times 10 to the minus 18. Human cell in your body, 10 to the minus 13 kilogram. Raindrop, 10 to the minus 6. Paper clip, 10 to the minus 3 kilogram. 2 dozen eggs, 10 to the 0 kilogram, approximately 1 kilogram. Human, we are roughly of the order of 10 to the second kilogram, because roughly we are around 100 kilogram. Then you get whale, 10 to the 5th kilogram. And then we start going into the realm of the stellar stuff, the outer space. We've got the Halley's Comet, 10 to the 15 kilogram. So now we're getting really big and heavy. Mountain, 2 times 10 to the 18 kilogram. Moon, 6 times 10 to the 22. We mentioned that on Monday's lecture. Earth, 6 times 10 to the 24. Sun, 2 times 10 to the 30. Then we start seeing other things that are even heavier than that. Type O star, later on in the course we will learn that these are bigger and brighter stars than the sun. They're called type O stars. 2 times 10 to the 32 kilogram. Then we will also be learning about globular clusters, 10 to the 35 kilogram. Dwarf galaxy, 10 to the 39 kilogram. Milky Way galaxy, 2 times 10 to the 42. And then you can keep going, because as we will learn today, when you cluster galaxies together, they're called galaxy clusters. So if the mass of those is going to be the mass of a bunch of galaxies put together. And so you can keep getting heavier and heavier and heavier. So this gives you a little bit of a feeling for the whole range of masses, and then how scientific notation is used in them. Okay, now let's get into, we're going to talk about the AU, the first thing. So I'll put this slide up. The AU stands for 1 astronomical unit, okay? 1 astronomical unit, and it is the average distance between the Earth and the Sun, okay? So as you see in this slide, you see, so the Earth and the Sun, and of course you've got Venus here, and then you've got Mercury here. So what we're doing is the distance between the Earth and the Sun, we're using as a standard of measure when it comes to big distances. And then we're calling that astronomical unit. And then over here in this picture, it shows you the Earth and the Moon. Well, the Moon's distance to the Earth is much closer than 1 AU, because the Moon basically is going around the Earth very, very close to the Earth as compared to what Earth's distance to the Sun is. So Moon's distance from the Earth you probably wouldn't say it in terms of AUs. You would more say in terms of miles or kilometers, okay? So AUs is more used for planet distances to stars, okay? So what's the main usefulness of AU? It is useful in writing planetary distances to the sun, not only for our solar system, but for other solar systems, okay? That's their main use. So whenever we discover a planet, one of the first things we want to do is mention and find out what is the distance of that planet from its star, okay? And then we do the calculations, and then we state the distance in miles, kilometers, and also in AUs. Okay, what is 1 AU equal to? This distance? Quite a huge distance, right? 93 million miles. Remember on Monday I said 1 mile is 1.6 kilometers. So if you multiply this by 1.6, you get 150. So in terms of kilometers, 150 million kilometers. In terms of miles, 93 million miles. And again, if you want to express this in scientific notation, you would do your 150 you see, remember how many zeros is a million? 6, right? 1, 2, 3, 4, 5, 6, right? So you get 150 and then 6, and then if you want to write this in terms of scientific, go 1, 2, 3, 4, 5, 6, 7, 8. 1.5 times 10 to the 8 kilometers, right? Yeah, you always put the decimal right after the first number. How many numbers that you have to go back? Yeah, okay. A lot of times if you look at data tables, they will also mention the distance in meters, not kilometers. So 1 kilometer is how many meters? 1,000. Remember the symbols we learned? Kilo, mega, giga, you know, and then the trillion was tera, right? So 1 kilometer is 1,000 meters. So if you multiply 1,000, 10 to the 8, basically you're adding 3 more zeros on top of this, right? So you're going to get 1.5 times 10 to the 11th meters. So all of these are different ways of stating the 1 AU. 1.5 times 10 to the 8, 1.5 times 10 to the 11th, 150 million. So if someone was asking to you, the easier way is just to say it 150 million kilometers, 93 million miles. But if you were writing it, this is the more official way of writing it. Okay. Remember the other day we also learned that it takes light how many minutes to get to the Earth from the sun? 8. So the other ways to say the distance of the Earth from the sun is to say 8 light minutes. The Earth is 8 light minutes from the sun. This is equivalent to 8 light minutes. Okay? So when we get to this part of the slide, we're going to be talking about something known as the unit of the light year. So light minutes is also a unit of distance. So when I say a planet is 8 light minutes from the sun, that means it's taking light literally 8 minutes to traverse that path, you see? So that's also 1 AU. Okay, so if you look at the back of the book, at the table, you will see the distance of planets written from the sun. Sort of towards the end of the book, there's this, what they call appendix. And table C-1, they give you the distances of planets from the sun, and they give it to you in 2 units, one in kilometers, one in AUs. So in AU is the one that I like in AU, 0.38, Mercury 0.38 AU. Venus, 0.72 AU. Earth, of course, by definition, Earth is 1 AU, you know. Mars, 1.52 AU. I added this one myself because after Mars comes what? Between Mars and Jupiter comes the asteroid belt, right? What is the largest asteroid in the asteroid belt? It's named Ceres, Ceres. It is also the first discovered asteroid. It's the largest one, first discovered asteroid. And the distance of Ceres from the Sun, 2.76 AUs. You see? The next one after that, Jupiter. It kind of comes from the same word from which we get the word cereal, the god of harvest and wheat. And we say cereal from that, you know. Jupiter, 5.2 AU. Saturn, 9.5 AU. Uranus, 19.19 AU. Neptune, 30 AU. You see? And then up to Neptune is where we've kind of ended the planets. Remember, we used to call Pluto a planet, but now it's been, demoted to the status of dwarf planet. Okay, I will mention throughout the semester. I will mention some of the reasons why it's demoted. You know, Pluto, in terms of size-wise, looks and feels more like the other planets in the outer solar system. There's other planets. One of them is called Planet X. There is other planets that are farther away than Neptune, many of them. Pluto has the feel and size of those planets. So one of the reasons it got demoted was when we started discovering those other planets, we said, hey, you know what, Pluto should be going in that category. So we started calling those dwarf planets. So Pluto is 39 AU. This other planet is 67 AU. So if we wanted to visualize this, we can say, write down everyone got to sign in? Okay, I'll just pass it around again, just make sure everyone gets a chance, whoever hasn't. So you might say, okay, what's the usefulness of the AU? Yeah, we've learned a bunch of numbers, but to me, I think it's very useful because it gives you a visual of understanding what the solar system looks like, you know? So if I were to lift this up, imagine I were to draw the sun here. Imagine drawing the sun here. And let's say let's say this is the Earth. You know? So by saying Mercury is 0.38 AU, what am I saying? It's 38% of the distance from the sun to the Earth. You know, so Mercury would be halfway would be here. Mercury would be roughly here. You see? Then Venus, 72% of the distance, 0.72. So Venus probably somewhere here. And of course, they're all going around the sun, but I'm just drawing them in a linear line, you know. 1.5 AU for Mars. So 1, and then another half would be somewhere about here. So which one is closer to us, Venus or Mars? Yeah. Which one is closer to us, Mars or Mercury? Now, I should have done this a little bit closer. Because this distance is what? If you subtract 1.5 minus 1, you get a half, right? So this one is about a 0.52 AU. And then from the Earth to Mars, to Mercury is what? 1 minus 0.38, that's 0.62. And then from Earth to Venus is what? 1 minus 0.72 is 0.28. So roughly speaking, you see 0.28, 52, what ratio is that? 52 divided by 28? About 2, roughly, right? 28 doubled is 56, so let's just ballpark it. You could say 2, twice. So Venus is twice as close to us as Mars is, okay? So all other things being equal, if you're trying to send a satellite to Venus, trying to send a satellite to Mars, which one's going to get there faster? Venus. And how much faster? Probably about twice as fast. You see that? But of course, that's not the general rule. It depends where is Venus in its path. Depends on other factors. So I'm not going to say it's always going to be like that, but it's going to be about twice as fast. And in terms of Mars and Mercury, which one's better? This is 50 to 6. So Mars is closer by a ratio of 6 to 5. So about 6 to 5 ratio is 1.2. So Mars is closer to us by 120%. If you change this to a percentage. So Mars is closer to us by a ratio of 120% to Mercury. So again, we should be able to get to Mars quicker. Okay, other than that, you get the Ceres asteroid belt. So here's one AU, here's another one. That's 2. And then roughly about here, you got the Ceres. You see? Asteroid belt, the biggest asteroid. But of course, you got other asteroids. And they're all going around the sun, right? And then what else you have? Then you have Jupiter. So that's 2. 3 would be somewhere here. Then 4 would be somewhere here. And then 5 would be somewhere here. Jupiter. Okay. Now, one of the things you notice quickly is what? The gap between them is starting to get bigger, right? More empty space here. So definitely it's going to take a lot longer to get to Jupiter. Then after Jupiter, 9.5 AU. So if I don't want to have to count back from the sun, I could just take the difference between the two. So 9 minus 5, roughly 4, right? So I got to go from here 4, 1, 2, 3, 4. So Saturn will be in the middle of the slideshow. Okay. And then after that, from 9 to 19 is 10. 1, 2, 3, 4, 5, 6, 7, 8. Now you see what's happening is you got Uranus is there. And then right Neptune, it's going to be outside of the room, you know. So if we scale it, you'll just go. So the distance got bigger. And then after that, another 9. And then after that, a lot more, you see. So as you see here, the usefulness of the AU is what? It gives you a good picture of where they're located and what the scale of the solar system is. You see? So you can scale it correctly. This would be a good project to do with if you're teaching like a junior high science class, have the kids get a poster board and then give them these numbers and then have them draw a scaled model of the solar system. So not just sun, earth, we all know the order, but we want the kids to learn the distances between them, and then one of the things that they will see is that the terrestrial planets are so close to the sun. When you get to the gaseous planets, they're much, much farther away, much, much spaced out, you see. So one of the purposes of the AU it gives you a scaled model of the solar system. See, if I put this picture up now, you see these kinds of pictures all the time, you know, in books and in magazines or something like this. So based on what we just learned, is this a scale model? So you see here, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus. Well, I don't think so. It doesn't look scaled, because if this is one AU, then Jupiter should be 5 of those, right? 1, 2, 3, 4, 5. Jupiter should be here, you see. And of course, Neptune, Saturn shouldn't even be in the picture, you know. So if they really wanted to make this a scaled picture, what they should have done is Mercury should be right there, Venus should be right there close, Earth should barely be here, you know, and then they could squeeze everything in, and then they can maybe show. But in order for everyone to be able to see it visually, they're making it like this so that you can see, at least see the planets, you know. But definitely it's not a scaled model. So they're just showing you the asteroid belt, comet, just to get to see what's there, you know.